think you might want that. Quick little nap. All right, my friends, let's settle in. As Lou said, we need to settle in. I think Lou wants something different. Just taking a minute to stop doing whatever you're doing and come into the room, whatever that means for you. Picking some particular sense or your breath. Those are all great places to hook on. How much can you let go of in just 5 or 6 breaths? Gently bringing yourself back to our room together, our shared space. I've got some stuff to hand back to you. I like doing this after that part of things. So this is the direction field homework. Let me just make sure I got them all here. So much shit. Okay. Why is there no grade on Kleenex? Well, I didn't add up the points. Sorry, Courtney. I'm gonna do this live here. And then I gotta take a photo of it. Well, I can't do that.
I think I saw the grade in world class.
What's that?
I think I saw the grade was
Is
posted.
it? I hope it was what's about to come out here. Let's see. So, well, we'll find out. And if not, I'm just gonna write this down here. Cool. That would have happened there?
I think so.
Okay, cool, great. Just didn't write it up. Okay.
Let's see. Oh, this is Lou.
Ms. Lou.
Thank you. And then
Brandon.
and did you get my email?
Yes, I
Okay.
just replied to it.
Okay, cool, awesome. Let's touch base right after class.
Okay.
Thank you. Okay, friends. So, yes.
I'll give it 9.
Oh, good. That's good to know.
Thanks, Brian.
Thank you. Let's see, who is that? Oh! See, okay, yes. Yeah, thank you. That isn't you. Where the hell is yours? Because I graded it seconds before class. I got it. Well, I'll hook you up before you leave here. I don't know what happened to it. Oh, look at that. There we go. And actually, the grade improved too, so that's
Great,
good.
thank you.
Alrighty, friends. So is there anything you would like to talk about just before I do my little spiel? Let's get some details out of the way about important things. So exam 1 is next Monday. Currently, the only potential would be to push it to Wednesday just based on how things might be going. But I think that seems reasonable. So, exam 1, there are review materials up. There's a review web work that is up. completing this will pay off in terms of bonus points towards your exam. So if you complete this with 100%, it's due like 15 minutes before class starts on Monday. If you complete this, I will give you some bonus. I'm not sure what that is yet, but it'll be worth your while. I'll find out. I'll figure it out. Where am I going to find it out? It's like right up in my head. I just haven't thought about what a reasonable amount is yet. So review web work, and then this is also possible exam extra credit for you. Also, I've got a few problems that I want to give you, and I think that I might have those written here in me notebook. Find me notebook. And maybe I'll just put these up on World Class actually, so I don't just waste time and so forth and etc. But here's what's going to be on there. Covers separable DEs, separable DEs, linear DEs, that's with the integrating factors, and autonomous differential equations. With these, there's going to be things associated like the flow line and bifurcations. And we're going to spend some time talking about that today. Bifurcations and stability. Those three things all go together. And then just direction fields for an arbitrary first order. So there's a little bit of some of this stuff in the web work, but I'm going to add some extra problems and solutions to give you plenty to review with. Does this sound right? Does this sound like what we'd expect to be? I mean, basically, it's what's on the exam, stuff we covered. Pretty straightforward. My exams are always much easier than the homework. So the stuff, web work is brutal, the exam's not brutal. Just most basic kinds of things you could imagine. So I'm not trying to get really nitty-gritty on those. Let's go back to a problem I left you off with. This one, and then this one. And I said, sketch the bifurcation diagram. I didn't give you a whole lot of different ways to approach this problem. So I wanted to start off the hour talking about different ways to actually do that. And so let's start off with maybe this one up here, because I think it's a little easier to see. Let me outline the process for you too, just in case you're not quite sure where to start in this. Sketch, so here's our problem. Sketch the bifurcation diagram, which means you understand stability and flow lines and all that stuff. So what this means though is sketch a diagram of equilibrium solutions, and those are when x dot equals 0. So the x coordinates when x dot equals 0. Sketch a diagram of the equilibrium solutions for all parameter values. And lambda is our parameter. So that's what we want to do, really have a complete understanding, have every flow diagram somehow represented in a single picture. Does this sound good so far? Hopefully this doesn't sound alien, right? Okay, good. So, step one, I'm going to give you a couple routes, is step one, here are some possible first moves. So one thing we could do is treat the equilibrium equation. And I'll just kind of work with this example where I have x dot equals 0. So I'm going to say 0 equals lambda x minus x cubed as two separate equations. And we are looking for intersections. So let me show you what I mean as soon as I get this written out. We are looking for intersections and how they change as this lambda changes. As lambda changes. Cool, so what do I mean by two separate equations? Well, I'm just gonna add x cubed to both sides. So this equation can be written like this. Lambda x equals x cubed. This really kind of breaks the problem down into two simpler things, each of which I understand a lot better than when they're put together like that. Most people can't do a graph of that in their head, but they can graph this and they can graph this. So in other words, I'm looking at where the x cubed graph, so this is, and this should actually be a little flatter. Let me make it look more like x cubed. That's an x cubed. It's still pretty, I don't like it, but I'm gonna stick with it. That's my x cubed graph. And lambda x, so this guy here is this. Lambda x is aligned with slope lambda. So I'm gonna draw that in here as well. Let's start off with it being negative. Wow, my God. There we go. So there's lambda x, and in this particular representation, lambda is negative here. But what we're gonna do is imagine how do these two things intersect as that slope changes. And the slope is our parameter. So when I start off here, notice that I've got just a single intersection at 0. So breaking it down like this really, really can help. So notice some things. Notice when lambda is less than 0, the only intersection is at x equals 0. So that means when lambda is less than 0, remember what your bifurcation diagram looks like. You've got your parameter on the horizontal, and you've got your equilibrium on the vertical. Oh, oh man, God, I feel so old. I think I just hurt my back doing what? Not much, crawling around on the floor in front of a whiteboard. So when lambda is negative, I've got just a single equilibrium solution. How could I determine its stability? So I'm making this line here. I'm going to leave it solid if that's a stable equilibrium. I'm going to dot it or dash it if that's an unstable equilibrium. Well, look at how x dot is computed. X dot equals the line minus the cubic. All right, just go back to the original problem, right up there at the top. It's the line output minus the cubic. So when I come down here, I just think to myself, I've got a positive thing minus a negative thing. What will be the sign of that? Positive, right? I've got a positive minus a negative. So here, the x dot is positive in this region because it's something big minus something lesser. That means I have flow in the positive direction. So we have flow like this. Does that make sense? And then over here, they reverse. You can see here I've got something that's negative minus something that's positive. In other words, a lesser thing minus a bigger thing, that's a negative flow. So over here, I have a negative flow. And that means that 0 is stable. So leaving it nice and solid like this is the right thing to do. So I've got a solid, stable equilibrium up until lambda equals 0. Let me stop. You let me know if this is feeling okay. Yes. Yeah.
Do you mind just going over the left and right side of the graph, how you got x is greater than less than 0?
Yeah, so this is x dot here. So x dot is defined as the lambda x minus x cubed. So over here, this is the lambda x curve. Over here, lambda x is a positive output, and x cubed is negative. So what I'm gonna have here is a positive number minus a negative number, and that's a positive.
Okay.
Does that make sense?
Yeah.
Yeah, and then over here, it's really the reverse. You've got the line, which is a lesser value than the x cubed, so when you take that minus that, you get a negative number. Sound good?
Yeah.
Cool, awesome, thank you for verifying that. At the moment we hit lambda equals 0, let's take a look at that moment, because that's actually our bifurcation point where things change. So at lambda equals 0, and you might want to draw separate diagrams. Lambda x looks like this, and the x cubed still looks like this. It's really flat right there, so there's the x cubed. Still only one intersection, but that is about to change. The minute this lambda becomes slightly positive, we all of a sudden have 2 intersections. 3, sorry, because we still have the one in the middle. So the minute this line tilts above horizontal, it suddenly starts to nick this graph right here. So we've got this solution, which would be some sort of equilibrium, and this solution, which would be another equilibrium. And so we have 2 things, and notice how they would be born. At first, they would intersect close to 0, and then as this slope increases, they move further and further apart. Come in way inside here, you've got an intersection like here and here. So 2 intersections are born as soon as lambda becomes positive, and so I have these 2 branches that come off of here, and I also have that middle branch as well. So all I'm putting here is, where are my equilibria? And so let's just in case this isn't quite making sense, if lambda equals 1, look what we have. We have x dot equals x minus x cubed. You could factor that. And you see that you've got 3 solutions, 0, 1, and negative 1. And so those would be over here. So for example, if this was the lambda equals 1, I've got 0, 1, and negative 1 as my equilibrium solutions. So the way to think about it, keep in mind, this is a bunch of flow lines. This is a bunch of just the flow lines where we have equilibrium, and they're all stacked together as a movie, essentially. Each slice is a frame. So now we have to figure out stability, but we can do that in the same way that we did before. So let's come back. Now I'm at lambda is positive. So I've got this. That's my upper equilibrium. This is my lower one. And I've still got 0. You come back to, what is the equation doing? It's working out lambda x, so the line minus the cubic. And that's how I will determine if I'm positive or negative on x dot. So this is flow direction. That's your x dot. So here, let's go here. I've got a curve lambda x is underneath x cubed. So what will happen when I take that minus x cubed? Is that positive or negative? This minus that?
Negative.
Negative, right? Something minus something bigger gives you a negative. So what we have here is flow toward that equilibrium. So kind of, we can even mark it off here kind of in a way. I flow toward that thing in that slice. And then notice that they flip. Here I've got line minus cubic. And so that's a positive because the line's on top, right? Line minus cubic, and I'm doing vertical distance. Everything flips over here, so what was positive over here becomes negative, and then here we've got lambda above the cubic, we've got lambda x above the cubic, so when we subtract we get a positive. So here I've got a stable equilibrium, a stable, and the center becomes unstable. So what we have in our diagram is this is stable, and this becomes unstable at the bifurcation point. And I have what's called a pitchfork bifurcation. So these are called pitchfork bifurcation. And this has a very special flavor. This is called a supercritical. And there's also a subcritical, which is that other one. The super refers to when does the good stuff happen in relation to the bifurcation point. So if it happens after the bifurcation, all the awesomeness, that's super. So this is after bifurcation. And this one here, if you actually sketch this dude out, it looks like this. It's actually kind of the reverse. You might want to check yourself out on this. It's the reverse in every way. It's two unstable branches and a stable come together to be unstable. So that is this one here, and that is a subcritical pitchfork. Because underneath the bifurcation is where all the interesting equilibria are. And then after that, things become a little boring. So this is just exactly what happens in that example I started with. Think about the first example we talked about, which was the semi-rigid compressed beam. We had our beam, and I had a load coming down on that. Let's say lambda represents our load. So for quite a while, the beam can flex, but it's pretty stiff. So as this load is being pressed down, it does its job. It's doing an okay job up till the critical load, so it's stable. Up until there's too much, so let's call this critical load here. Critical load. That's the bifurcation point. As soon as that load becomes critical, it could buckle that way, it could buckle this way. And once it buckles, that's a stable position. It's not gonna unbuckle, it's not gonna buckle again. But if it maintains its rigidity and doesn't buckle, man, you're in a precarious situation because it is just waiting to buckle. So that's what the instability means here in that situation. So I'll put a little note here. So this is buckled. This is buckled. And this is not buckled, but pretty ready to, but precarious. This is not buckled and stable. But stable. Cool. Yes, Lou.
So the opposite would be that it's ready to buckle, it's ready to buckle, it's ready to buckle, and then suddenly it's ready to buckle and it's stable, like the.
I'm sorry. So where are we asking? Are you asking questions about this subcritical? This is a little weirder. I don't have a good example for this one. So everything I'm saying here is the supercritical is the one. I'll come up with an example. I think I have to go into chemistry, which is not my forte. Carefully avoiding that. I'll get you an example. Any other questions on this? No? Okay. Let me show you how you could do these bifurcation diagrams for something a little freakier. So, so I think I was going to show you two methods. Here's the other method, and then we'll pull out the computer, and I'll show you how to manifest both of these routes. So, alternate method. Honestly, I usually do both of these because it just helps me put the pictures together in my head, because sometimes these pictures are hard to visualize. So the alternate method is graph y equals lambda x minus x cubed. And we know that this just represents x dot. And use a parametric tool. Use Desmos with a parameter. So what I mean is we're going to add in this extra variable here, and Desmos is going to give us a little slider for lambda, and as we move it, it will live action change the graph. It's incredible. Katrina was in my, where we were looking at this together, yeah. So it really can be a powerful way to do all of this. So what I mean here is, let's say I'm at the lambda is greater than 0 mark. What I would see is something that looks like this. And this here, you could actually figure out that's square root of lambda, that's negative square root of lambda. And then I've got 0. And so what I do is then realize, oh, y is the direction. So that's positive, negative, positive, negative. Now it's just the flow diagrams, and I'm analyzing them like you've already done. So notice here we've got unstable, whoa, wait, I got that S backwards, don't I? Yes, woo, scary. Stable, unstable, stable, just like our picture over there. And as you tweak the lambda, you can watch these move apart and see that basic shape there. So let's do that. And then let me show you how we can do some cooler things. Let's see. Does it seem like that's, it doesn't sound like that's doing things, does it? Lou, would you mind checking that out for me? I appreciate you, thank you.
It says it's on.
Okay.
Well, it says it's on standby.
Yeah, there's no blinding light coming through. Or can you just hit it?
I'll just hit the button.
Yeah, hit the power button. There we go. Hey, green. I like it. Looks good. And I'll start getting some stuff in here. So Desmos is a wonderful friend. It would be hard to do this stuff on a graphing calculator. Somewhat painful as well. So let's take a look here. Here's my lambda x. I'm just going to call it mx. Now watch, as soon as I type a weird letter like not x or y, it says add slider. So you click on the slider. And then you can just move this and watch it change. That's really lovely. I'm going to add that second equation, which was just the x cubed. Ha ha, wonderful. Let's zoom in. And you might want to actually adjust how many steps you have. So I like a 0.25, 4 steps per whatever. And let's say there's 5, and then we'll just do -5. Okay, cool. So that just gives me a little bit more control. So now we can see, here's lambda negative. Only intersection is at 0. as lambda becomes positive. There's lambda 0. The minute we become positive, suddenly two intersections are born, and we can watch those move further away from each other as lambda increases. Now watch, I can do this all actually in one fell swoop. So that's method 1, which I find very useful. But method 2 has its charms. So if I say mx minus x cubed here, that looks weird, so I didn't type something right. There's an extra x, there we go. I can still do the same thing. So lambda negative, I've only got one equilibrium. It's at 0. It's negative flow on the right and positive flow on the left, so that is a stable equilibrium. As we slowly increase, notice that these two little, I want finer, I want it even finer, so like 0.05. There we go. I like my movie smooth. So there we go. You can watch those two new equilibria be born and move further and further away from each other. So this is what I would recommend. You're not going to be able to do this on the exam because you're not going to have internet access. But maybe I'll tell you some stuff up ahead of time that you could get ready and prepare yourself for. Maybe a bifurcation diagram or two. But let's say I have an interesting one, and I gave this to a friend. I think I gave this to a friend. Is that what I gave you, friend? Is this the...
Let me see. I took a picture of it.
Cool, okay. It sounds like me.
Yeah, I think so.
Yeah? Okay. So let's look at the two ways we could do this. One is plot lambda x, which is a line. That's super low-hanging fruit. And then I'm actually interested where that line intersects e to the x. So here's e to the x. That's one right there. So clearly for a lot of lambda, there's no equilibrium because these two have to intersect to have that be true. So for a lot of lambda, I don't have anything. And then at some point, all of a sudden, I will be tangent to it. Imagine that actually was a line through the origin. And then as lambda increases, all of a sudden I have one intersection at a point like that. So let's see if we can see this and believe this over here. So let's do it the first route. We're going to have mx, and then down here I'm going to have e to the x. Cool. Let's back out so we can see. Oh, actually there is an equilibrium over there. I don't know what I was talking about. That's nice. I'm glad I graphed this. So yeah, when we have a negative slope, negative lambda, I've got one intersection. And it looks like as lambda goes to negative infinity, that intersection approaches 1. So we've got this one equilibrium that as lambda increases, that thing becomes super negative and rockets all the way out to negative infinity. And then there's no equilibrium for a while. And then suddenly, I've got the birth of a single, but then this thing should actually intersect twice. So now we've got two equilibrium being born there. So let's see if we can, let's at least just focus on the lambda positive part. The lambda negative is a little challenging to draw, and I don't want to confuse things. So let's just say we're working with lambda, and we're going to stick with lambda positive. So what happened was, at some point, this graph intersected this one. And let's see if we can just imagine where that was or estimate where it was. Let's see. So it looks like I've kind of got a feeling when the slope is e, because that's hella close to e. I think when the slope is e, it's just perfect. So what we have is no equilibrium, and then suddenly when lambda equals e, an equilibrium is born. And that equilibrium will be like, well, it kind of looks like e, right? Roughly, right? Seems to be about 2.7. So if this is my equilibrium here, my equilibrium solutions, and this is E, I think it's kind of going right at E. I think. I'll verify this and let you all know, because now I actually want to sit down and see that for myself. But then that one splits as we keep going onward. So let's draw the quick version of this picture, because we're going to see two branches coming like this. It's a blue sky bifurcation. And how did that picture come about? Well, we have e to the x, and then we have this line here intersecting e to the x in two spots. So here, and remember, we've got line minus e to the x. So down here, e to the x is on top, line is on the bottom. Wherever that is, this is going to be a negative quantity. Line minus something above the line. And then over here, this is going to become positive. We've got line minus something underneath the line. And then that's going to go up to this guy. And then that flips. So it looks like the one with the larger x coordinate is stable and the one with the lesser x coordinate is unstable. And now we have a rough sense of the bifurcation diagram. Now there's like a weird ass part over here that's kind of weird. I don't want to get into it right now. Katrina, I'm sorry I gave you such a weird ass problem.
No, it's okay.
Does that make sense?
Yeah.
Yeah, question.
Can you go back to like right when it, because I don't know if it looks like E on both sides.
Yeah. So I'm sorry. So where were you asking me to look at?
Like you know how you put it at E?
Right. Like right there when it.
Yeah, it doesn't look like it's at E on the x-axis to me.
So I guess I was looking. Yeah, let's take
Like
a look.
on the y-axis, I could see that. Maybe. But you're not even. At
Oh, you're
2.
right. Yeah, what the hell was I saying there? I don't know. Oh, because, so the reason I said E is because it's not coming from this x coordinate down here. It's coming from just the slope that I'm
Yeah,
using.
okay.
So the slope was about 2.7. And then, yeah, but you're right though, like where that happened is not E at all, is it? It's more like 1.
Yeah.
So I think you're right. I think this is actually 1. Thanks. Yes. Your intuition that something was wrong, I think, is spot on. Yeah. Let's do it the other way to see, because sometimes it is easier to see when we put it all together. So let's just look at e to the x here. And then let's get rid of this dude. Ah, so that's, there we go. It's clear as day, actually now. So notice that when the slope, as the slope approaches E, right at that moment we start to break over at 1. So that equilibrium at 1 starts to spread. And notice how it's kind of keeps cruising to the right, but becomes asymptotic to some number on the left. So like this branch down here is becoming asymptotic while this one is rocketing off. Some things to practice with this week. I'll give you some practice problems to work with. I want to show you something insane though first. That's really cool. One of my favorite bifurcations in the world. And it actually has relevance to our perception, our perceptual system. So let me just show you a really cool one. And then we'll just probably just take some time to just start working on stuff in here. But this one is x dot equals lambda x plus x cubed minus x to the 5th. So it looks a lot like one of those pitchforks. Looks a lot like the one I was calling the subcritical pitchfork, but it's got this higher order term. When x is positive, this is a very large, this is a negative number. When x is negative, this is a positive number. So it's kind of working against wherever we're at. It's like a very strong force introduced into the system. let's see if we can come up with the diagram by just using the techniques we talked about today. So I'm going to use this one here where I take mx and then I'm just literally going to type this whole thing into there. So I'm going to graph out y equals lambda x plus x cubed minus x to the fifth. And what we're interested in is where is this zero? Because that'll be an equilibrium solution. But we can really see there's some amazing stuff that's going to happen in here. So we've got mx plus x cubed minus x to the fifth. Okay, let me back up. So we've got a weird ass thing there. And let's get lambda down like this. Okay, so as lambda is negative, you see we've only got one equilibrium. Do you see that weird kinking starting to happen in the line? Yeah, that tells you there's some funkiness coming up. So as I get closer to zero, the kinkiness becomes even more profound. Let's get in here because there's some weird stuff that happens. Notice how I've got a little local max and local min forming there. And all of a sudden, there's my first change of state. I've got these two equilibria that form out here and here. And watch what's going to happen. Each one of those is going to split. Each one of those splits. And half of the split moves towards zero. See that? And the other split moves outward away from zero. And then we're back to just 3 equilibria. So look at that. How many equilibria do we have? 1, 5. All of a sudden, 5 are born right at that instant. 1, 2, 3, 4, 5. The 5 persists for a while and then goes back to 3, and it's 3 from there on out. So what the heck could this picture look like? It's pretty intense. So let's get just a winged up version of it. So we started off with that 1 equilibrium. Let's just go through this again. When lambda is negative, I've just got 1. Is that stable or unstable? Stable. You know, because over here, I've got negative flow, so I'm flowing toward the origin. Over here, I've got positive flow, I'm flowing toward the origin. So I've got a stable equilibrium that exists for a long time. And then all of a sudden, right here at some critical, let's just call it lambda naught, I've got these 2 that just kind of come in out away from the current one. See how that one's just all of a sudden born? And let's do this so we can actually analyze what happens. So there's an equilibrium born above and below 0. And then that equilibrium splits. So at this point, at some critical value, whatever that slope was, I've got this thing that's born here and there. The upper one, so this is the one on the top, I've got 2 branches up here, is a negative flow and a positive flow, so it's stable, and then this one will be unstable. Stable, unstable, still stable, and then this one here is positive, so this will be unstable, and then this one will be stable again. So we've got something that looks like this. Stable, unstable, stable, unstable. And then those 2 unstable ones, so the ones that are closest to 0, they move, they keep moving to 0. Look at how they come towards 0 and then collide in an instant. So what we see is this one comes down this way, this one comes up this way, and they collide right there. Now, we all along, let's come back and make sure that this guy was stable in the center. So let's see, so yeah, that's stable at 0. And then these guys collide. So I'm gonna make this nice and solid. This one keeps on cruising. This one keeps on cruising. And right after we get past this point right here, we've only got the 3 of them all together. And then this one is now unstable. Positive flow, negative flow. So that one became 0. So this is one of my favorites. That's a weird ass picture. Why is it even relevant? Because a physical system that had a bifurcation diagram like this would exemplify a particular phenomenon known as hysteresis. Non-reversibility. Any physics, chemistry folks in here can help me with hysteresis, like an example? Yeah.
Would I guess like I don't know.
It's cool. It's cool. You need something where you've got this control knob, lambda, and when you turn it up to a certain point, you're not guaranteed that turning it back down will reverse your situation. Here's what I mean. So this is stable over here. If you veer a little bit off the path here, you're actually just pushed back toward it. So this is stable.
It's like trying to get like toothpaste back in the
Maybe something like that. Yeah, I like that. So then the toothpaste comes all out right here. And so you're maintaining stability, but then you get out to here, and you could maintain that stability, but if you're a hair off, you fly up to one of these equilibriums. So realize that we've got that unstable that's trying to force you to one of these 2 branches. Then when you reverse the situation, so you turn your knob up, you're like this, some sort of noise in the system sends you up here. When you turn back the knob, you're not here anymore, you're way up here or you're way down here. So when you come back, you actually follow one of these branches. Let's say it's the top one. The minute I get to here, I would drop down, there's nowhere to go. I drop suddenly and rapidly to that equilibrium, and then I can just keep repeating. So if I come back up, I can almost get this kind of looping behavior if I just kept turning this knob up and down. But notice that, say this is temperature that this axis represents. This is a sudden jump in temperature, and then we get down here and there's a sudden drop in temperature. All the while, we were just kind of hoping to keep it at 0, but things got out of control. So my favorite example of this is a neurological example in the way that we process. And I think I put this up in our world class, but I'm just gonna, hysteresis, I just have to search for it like this. Let's see, so face, lady, and let's see if we can get it. There it is, fantastic. So check out this image. So this is an example of hysteresis in our perceptual system. And the way to think of this is, as you start here, you probably see a face. You might not. If you don't, you might be of great interest to psychiatrists and psychologists. But you see a face, like some Fred Flintstone-y kind of person. And the parameter is moving from left to right. So you keep following across here, you see face, still seeing the face because we started with the face. Our current equilibrium is that's our stable equilibrium. But then we get here and things start to morph, and then suddenly it snaps into this. Just all of a sudden, you're watching the transformation, you're like face, 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 lady. And then you try to reverse it. So when you move backwards, you don't do the sudden jump. You're actually at a new stable equilibrium. This is the upper branch. So as you come backwards, you can still see the figure of the woman. And then it snaps back into a face. So you've got these 2 equilibrium that as you move in either direction, they become unstable, and your perceptual system's trying to figure out what's going on. But it's working with the last information it had. and locking to that. And then you're here, you're back to face again, you come back, you have the same phenomenon. So can you kind of see how that's this here? It's like a history, it's history's sudden, unreversible changes. Anyway, that's all I wanted to tell you today. It's like one of my favorite DiffyQ stories. So, any questions, my friends, on this? We have like 22 minutes left of time together. Let's take this time to work on stuff. There's the web work. If you don't have your laptop, which Tara might not, I don't know. Oh, she'll got it right there. Okay, cool. Okay, awesome. Let's make sure that assignment's open.
Not yet.
It's not open yet? Let me fix that. Oh, what time does it open? Does it say?
1:30.
7 minutes. Wow, I was much faster than I thought I would be. Just do it. And I'll get you the details on how doing all those problems will benefit you. You can see all the secrets. So it should be called Exam 1 Review. There it is. And let's just make it 1. It opened at 1. Wunderbar. Should be good, should be good. I'm gonna go to the restroom break. I'll be right back. Just get me those and I'll hook you up, okay? Doesn't look like a question.
Yeah.
Seemed like it. Yeah.
I wish I secret this is my number. But then when I went
Oh,
to
did I
the-
not do it well? Did I miss?
I think you mistyped.
I think you're right. What was it supposed to be?
You wrote 44.
Well, then I might have put yours in someone else's, and vice versa. Yeah. Yeah, that doesn't look like it.
Yeah.
That's for sure.
No, I saw it. I was like, oh, wait.
As much as it takes, I take great pleasure in removing points from your
I know.
homework.
And then I had a question about this one too. 'Cause you gave me the extra credit, but it's just not
Yeah.
in here. I didn't know how that was going to work, so I was just like,
Oh,
well.
Wait, which extra?
On that one, there's the Pythagorean.
Oh,
triple one.
I didn't add that in there.
No.
No, I think that's because I was gonna make it a separate
Oh, okay.
thing, so I still need to, if you would give me that, please, cause you're the only person who did it.
Okay. Do you want the paper or?
Yeah, just
Okay.
anything that would remind me that
Okay.
this happened.
Okay.
Gotta make sure you have more than 100%, right?
I was just curious. I wasn't.
No, I know you're not. But that would be the net effect. Please send me an email.
Okay, yeah.
Email
That would
that just
probably-
says, diffieqec.
No, this is for.
Oh, then that one,
Okay.
then. Yes, thank
You want me to send you an email about?
Please,
the
yeah,
other one? Okay.
Modern Geo EC, please.